So we're going to talk a little bit about some kind of basic kind of math language issues. You see something that looks like this. You have to know how to interpret this. And while there are conventions, common ways to do it, there's no right or wrong way. There's just you have to know what is expected. So we have this idea that this convention we use, which is that multiplication and division have a higher priority. If you see this here, it's like there are implied parentheses. I mean, we see this question asked on core all the time. What is this equal? And some people say, well, 3 plus 6 is 9 is 36. Some will say 24 plus 3 is 27. And again, without context, without someone saying, well, this is how we're doing it, it's ambiguous. But we're typically going to do this. We're going to assume that multiplication is more important than addition and subtraction. Okay, so now we're still left with a problem here, right? Well, it won't matter in this case, but what order do you do addition and subtraction? Yes.
4 times 5 is not 4.
Did you hear about my deal with my calculus class?
No.
Yeah, if you find a bug, and you let me know, you get a chocolate truffle.
Do you have them?
No, I'm going to bring them in there. You just could have used it right now, huh? All right. So remind yourself, when I come in next week, you were owed one.
All right.
Thank you. Okay, so 3 plus 20 minus 6, that's fine. If I said 20 minus 6 plus 3 would turn out the same, but not always, right? So when we're dealing with addition and subtraction, we just go from left to right. And the same thing with multiplication and division. You saw well, it would certainly make a difference if I say 36 divided by 12. That's not the same as 36 divided by 4. That's 3, isn't it? So again, with division and multiplication, we go left to right. Now, none of this matters if you put parentheses. Okay, I can if I rewrite this way, right? There's no ambiguity, and so I encourage you when you're in a situation where it might be ambiguous, or you're not sure. You don't even have to remember these conventions. You can always put parentheses and make it perfectly clear. Right? Just that basics to reading math expressions. Okay, now here we come to a problem. These are all binary operations. Binary meaning 2, meaning they're 2 numbers. But we have a number of unary operations in math. Let me just point this out. This is not the same as this. And if any of you have like a TI calculator, oh, maybe not. Not this, yes. Okay. So if you look down here, there's a minus, and you look here, and there's a minus. And the difference is, this minus is a unary. It's just, I want to enter like -6. Now, you could always kind of make this a binary, putting a 0 in front of it, but with the calculator, you actually have to tell the calculator what you mean. And if you do the wrong one, sometimes they'll complain or they'll get confused. Thank you. All right, but we do have these unary operators. These are all called operators. And minus, can go on the 3, that means -3. I can have 4 squared. That's a unary operator, it's just exponentiation. But what happens when we have this? Actually, make it simple. Right. So the question is this -3 times -3, or is it -3 times 3? Here the result is very different. You get either 9 or -9. Now, this apparently is not as set in stone as I would like it to be. Your book, I think your book treats it this way. But I like to treat it this way. So your best bet when you're dealing with something ambiguous like this is to always use parentheses. You could write this as either -3 squared or -3 squared. And then there's no ambiguity. Right? There's no confusion about it. So important things to watch out for. Okay. For those of you who came in late, my notes disappeared. Thought I had them. Occasionally, when we're writing something out, we want to add another level. We could just add another set of parentheses to decide what goes on here. But we also will use square brackets. It's possible you may run into something where someone's using curly brackets, but this usually has a different purpose. It's usually not to differentiate this. You could use these if it's clear that's what you're doing. But usually we use these for other things. So again, the detail. All right. So there's this, like this, I call it common wisdom, that the Inuit people have like 50 different ways of saying the word snow. Because if you live up north, there maybe you make 50 different distinctions. In math, our version of snow, the thing we deal with a lot, is multiplication. So I could say 5 times 3. My hand is doing something different from what my brain is doing. 4 times 3, or you could write 4 times 3 with a little dot. You could use parentheses, either way. And when we get to using variables, we have we may just write that without any operator at all. We'll just put a number in front of a variable. Numbers in front of a variable like this have a special name. They're called coefficients. It's just 1F. These are all kind of language things, right? They're not like how to add or subtract or solve a problem. They're just understanding what we're writing. Okay. All right, so the next thing we want to talk about is we do want to talk about variables, which is x. Right, that's the most common variable we use. It's just meant as a placeholder, but typically it's a placeholder for something we don't know. So we might say, x plus 5 equals 6, and we want to know what x must be. Other common variables we will use x, y, z, and really you can use any letter, any single letter or combination. Sometimes we'll use a letter that has particular meaning. So if, for example, if you're doing finance, we might say future value, or FV equals present value, 1 times 1 plus interest, where these have specific meanings that in context you know. Physics or astronomy, we have F equals MA, force equals mass times acceleration. You just know these from context. In this class, and most math classes, we're going to stick with very generic variables like x and y. Sometimes we'll use a particular variable, different variable name for something in particular. Now, this should be distinguished from certain letters which are intended to have a specific meaning. Pi is just a Greek letter. But you'll almost always in math, when you see pi, it's that number, right? It's approximately 3.1415, so forth. This is a good example of something we call constant. Now, pi is a constant that we kind of know what it is. But often, when we're writing something in math, right, we'll see an equation like this: x squared plus x plus c equals 0. We have these letters, which will typically use A, B, and C. Sometimes we'll use K. We don't know what A is, but it's not the same as x. It's not something we're going to solve for. It's something that has some value that we may plug in later. And again, these are called constants. And that's to distinguish them from variables, things that change in value, or that we're going to search for a specific value for, we're going to solve for. All right. Sometimes there is notation in math that can be ambiguous. For example, if I write 3, comma 2. So one meaning of that is that's a point on a graph. I have some graph. This is the x coordinate, so 1, 2, 3. And this is the y coordinate, 1, 2, and it's a point. Right? But in other contexts, this is what we call an interval. We have a number line and 0, 1, 2, 3, and specifically what we mean is numbers. Well, actually, let me do it this way. You normally wouldn't use an interval with the numbers in the wrong direction, but here we mean numbers between 2 and 3. I mean, x is less than 3 and greater than 2. And this is actually called, when you have parentheses, it's called an open interval. We're not including 3 and 2 in it. We could write the same thing to include 2 and 3 like this, or even a half open, half closed interval, 2, 3. But these are just all numbers on a number line in between certain values. All right. Excuse me. Some other terminology. In this equation I have here, let me come up with something that looks a little more. Let's see what this figure on here. When we're adding up pieces like this, these pieces are called terms. They can consist of, again, a coefficient, and a variable, and we call this whole thing here an expression. It's just a mathematical expression. Again, you know, there could be parentheses to disambiguate what it means. Now, if you take an expression and you equate it with another expression, now we have an equation. Equation simply means we're equating two things. And this particular equation we might want to solve for x. We might want to find out which x's make this equation true. Sometimes that's not the case. If I said x plus y equals 3, well, you know, for every x, there's a y that will make this equation true. So it's not just a single value we're looking for. Not all equations will have a value, for example, that has to make any sense. If I write x plus 4 equals x plus 3, you can't come up with an x, a value of x that makes this true. So this is, if I gave this to you as a problem that said solve this, you would have to come back and say no solution. All right. All right, just a little bit more on this. A very typical thing we're going to do is we're going to write an equation that looks like this. Or it might be y equals x squared or y equals the square root of x. And again, we're associating values of x with y. We might want to graph this. We might want to, again, have a two-dimensional graph, and this could be our graph of x squared. However, in this context, we have a particular set of names here along this axis, the x-axis. We call this the independent variable, and we call y the dependent variable. Well, what do we mean by this? Typically, we're thinking we're varying x, we plug in an x, and we get a y. So x is kind of on its own, independent, but once you pick an x, you're kind of stuck with the y. It's dependent on the x. I don't think we'll do anything like this in this class, but you could have two independent variables. You could have y is equal to x plus z. Z could be like off in yet another dimension. Now this is contextual too, because if I wrote it this way, if I wrote x equals y squared minus y plus 2, I'm using y here as the independent. It's very rare we do that. We're almost always using x, just as convention. There's nothing absolute about it, though. All right. Okay, I want to just say a kind of a general thing here about learning math. How many people here have ever had someone ask them, are you a visual learner? Yeah, okay, right. Or maybe you're an auditory learner? No? I've even heard of kinesthetic learners. People have to get up and jump around. Okay. So I want to tell you just a little bit about this. There's no doubt that people may lean on one, what we call modality, more than the other. More than another. Now, as a practical matter, except people who are sight impaired, we're all very, very visual, right? That's just, evolution has made us aware of our surroundings. And however, again, some people, again, they may lean towards, auditory or, writing things down. The reason you probably run into this is because there's this idea out in education that if I want to teach to my class, I have to be aware of what kind of modalities they use, and I have to use those modalities. This is a very, very common idea, and I'm presenting it here because it's been entirely debunked. They have done sociological studies where they go into classrooms and they teach students in one modality or another, all this. And what they find is, sure, you may have something that you lean in one way or another, but it doesn't affect your ability to learn. The teacher's using a different modality. I suspect that's just because we're all naturally, convert whatever we see into the way we think. So, okay, that's just a little piece of trivia. All right, so what we're going to do now, I guess I had an example. here, just to show you what, you can tell me if this appeals to you. So I'm going to demonstrate here what we call the distributive law, right? The distributive law of multiplication over addition. And it says that 3 times 2 plus 4 is just 3 times 2 plus 3 times 4. I distribute this. Well, the kind of the visual version of that would be, well, I have 2, I have 4, and I'm going to multiply that by 3, right? Well, I can look at that as 3 times 2, 3 times 4. Now, maybe that appeals to someone here. I feel like I'm very visual, but to me, this is like, well, I guess when I was like in 2nd grade, this was useful. But right now, I don't have any problem with this. Right? It's pretty straightforward. Okay. Let's see here. All right. Okay. We're going to talk for a minute about numbers, what we call the real numbers. I think a couple of days ago, I put up a Venn diagram of, how numbers kind of fit together. We start with whole numbers, we go to integers, rational numbers, but we're going to talk about properties of all these numbers, the real numbers. And I suspect you've run into some of these properties before. Some of them you just know automatically, because they're so obvious. In particular, we're going to start talking about addition. And very high on the list is the associative property. So the associative property says if I have 3 numbers, I'll write this in a kind of a formal mathematical way. A, B, and C are members of the set real numbers. If they're members of the real numbers, then A plus B plus C is equal to A plus B plus C. Okay, I think we all kind of know that. It's just saying when you're adding numbers, when you're adding more than 2, it doesn't matter what order you add. So that's kind of high on the list. Next on the list is the commutative property. Anyone know what the commutative property is? Oh. It's also going to be like, oh yeah, of course, but I just didn't know the name, right? It says that A and B are real numbers, any real numbers. Then A plus B equals B plus A. that may seem really, really obvious, and sure enough, yeah, at this point it is. When we move further on in math, sometimes there are number systems that don't have this property. Oh, also, if you're ever at a party and you want to like act like you're like a math PhD, just call this the abelian property. Is that an abelian number system? It's just Abel was a famous mathematician, and he worked with commutative number systems. Okay. The next property I want to talk about is the inverse property. Oh, I don't think so. The inverse? Which do I want to do first? I want to talk about the identity property. I'm sorry. Better to do this first. Okay, so that just says if A is a real number, then A times the identity, A plus the identity, well, the identity we call 0 is A. There's a number that you can add to any other number if you get the number back. Now, again, that kind of sounds obvious, but it's really valuable to know that this one particular number has this very special property. And we have the inverse property. Says if we have, again, some A, which is a real number, then there exists an inverse. This is the math symbol that means that there exists an inverse, which we call minus A, such that A plus minus A equals the identity. Now, all right, all this stuff so far has been so simple, but I want to just show you right away why this is so important. We're going to look at a very simple equation. We'll just say x plus 5 equals 0. Now, this property tells me there's some value, in this case, it's minus 5. And I can add to x plus 5. I'm going to add it to this side too. Right? And I'm going to get x plus 0. And over here, of course, I get x minus 5. And of course, x plus 0 is just x, which is a long way of saying it's very, this property enables me to solve certain kinds of equations. Now, you might think, well, I learned that. I didn't really need the property. But this is kind of the way that we formalize it now. Okay. There's one more property which I don't think you need to know. But it's kind of like the first property. It's called closure. Anyone know what closure means in this case? Run into this. It's just so simple. It just says A and B are real numbers, and A plus B is a real number. In other words, you can take any two numbers, add them, you get a number. That's all. All right, so now all these are properties of addition, and we have very similar properties for multiplication. For the most part, they have the same names, right? I'm just going to abbreviate here. The associative property says A times B times C equals A times B times C. The commutative property says A times B equals B times A. The identity property says there's a number which we call 1 that I can multiply by any number and get that number. Now, there's a little difference here with the inverse property. If we have some number A, there's a number we can multiply it by. We sometimes will write it A inverse, but you're probably more used to us writing it as A times 1 over A. And that number equals the identity, which is 1. And again, this is really helpful. If we have some equation like 2x equals 4, it tells us there's some number, in this case 1/2, that we can multiply this by. We're going to multiply both sides by it. It kind of gets rid of this 2 here, right? This becomes 1. 1 times x is x. And so now we just need to do some calculation here to find out what x is. All right. Finally, now that we have both multiplication and addition properties, there's one more property which I mentioned earlier, which is the distributive property. And it says that if you have 3 numbers A, B, and C, that A times B plus C is just A times B plus A times C. And we use this a lot to manipulate equations to get them to solve them. All right, so this is very, very basic number facts. It's a little dry. That looks very dry. And this is our starting point. We're going to, we're not going to mention these very much, but they're going to be embedded in what we do, right? When we manipulate equations to solve them. These give us some rules that we're allowed to use on our number system. All right. All right. I think it was Thursday. We talked a lot about exponents and the rules for exponents. But we were talking about exponents and numbers. And we want to talk a little bit about how we use them with more general expressions. So, for example, I might have something like this, 3x squared. And one of our rules of exponents says that I can distribute this 2 over these, right? Over the number of the variable. So 3 squared times x squared, or 9 squared. Another example would be, you might have x plus 1 squared. Right? Well, that's x plus 1 times x plus 1. Now, when you're multiplying these are polynomials, very simple polynomials. If they're not simple, we use a method that looks a lot like long multiplication. Right? So if I said I want to multiply x squared plus 3x plus 2 times x plus 1, well, I just use the same method we learned for multiplying numbers. I say, well, 1 times 2 is 2. 1 times 3x is 3x. 1 times x squared is x squared. X times 2, again, I'm now moving over. We have 2x. X times 3x is 3x squared. X times x squared is x cubed. And then I add them. But for simple expressions like this, we have a, they come up really often, right? X times some coefficient plus some number, x times some coefficient. We have a little mnemonic. Does anyone know the mnemonic?
For what? What are we looking for?
A mnemonic. It's just a word that's going to help us remember how to do this. The word is FOIL. Any of you heard of FOIL before? Okay, some of you. Stands for first, outer, inner, last. So what does that mean? First means we multiply the two firsts. This x squares. And we multiply the outer, x, the inner, x, and then the lasts. 1 times 1. And then what you learn when you do this is that if both of these are the same, they're both x or x squared, the outer and the inner are going to look, they're going to have the same variable, right? So you can just immediately write down x plus x squared plus 2x plus 1. That's what FOIL is useful for. Later, when we do some factoring of these expressions, we're going to factor what we call quadratics. We'll use something called reverse FOIL, where what we're really doing is we're kind of trying something and then testing it with FOIL real quickly. So. Right. This next piece, covers this, and it's just so basic. I'm not sure if people really have any confusion about this, but we might have an expression with a variable in which we're asked to substitute for the variable. Right? It should be pretty straightforward. Let's say I say x equals -2. Wherever I find an x, I put in a -2. And then I just have some numbers I have to evaluate. -2 squared is 4, plus 5 is 9. If I give you another x equals 1, well, that's even easier. 1 squared is 1, plus 5 is 6. So that's something we're going, just a minor skill we're going to use. Sometimes the expressions are very extensive, and it's often good to not panic. So if I told you we're going to be substituting in here, and it's going to be oral quiz. You're going to have to stand up and answer. And I said, and you're sitting back there going, "Oh no!" Right? Who wants to volunteer? good. But now I say x equals 0. Okay. Anyone want to volunteer now? Oh, there. Yes.
It's just +1.
Yeah. Right. So don't panic. Right. Right. Now that you answered that here, how about this? X equal 1. Oh, well, that's a little bit. 4, 8, 7, 1, 4, 8, 11, 12. Lots of times there'll be problems where you're going to have to do this, and it's like, oh, well, it's not that hard. A little harder bit might be like x minus 1. It's still pretty simple. It's like if this is even, right, then it's just 1. It's odd, so it's negative. It's 4, negative 3, 4. So negative 6, 6 is 0. Ooh. If I had given you this as a equation, solve this equation, you would have guessed minus 1, you'd have found a solution. Okay. Yeah. Okay. Okay, I have a couple more examples of these. I'm going to let you try some of these. Have some paper handy. So the first one is absolute value of y minus x. And x equals 4 and y equals minus 6. Okay. While you're working on that, 1 plus 2z. We just about run out. Anyone have an answer for this?
2.
2. Okay. Let's see. Absolute value of negative 6 minus 4 is, uh-oh. Did I do something wrong? I don't think so.
Oh, never mind. I didn't know if there was an end.
Yeah, see now,
Okay.
good example. No fault here. We all do this. Math, you have to be really precise. Right? All you did is you mixed up one sign, right? Or maybe you didn't see it, so here we just off on the edge. All right. So minus 6, minus 4, minus 10, but absolute value, so it's 10. All right. What do we got here? Minus 2 plus. Anyone else get to this? 2 times 3 is 6. 5 times minus 2. Minus x times z minus 5 minus 3. Okay, so then we just have to work it out. Okay, now I know today was really kind of simple stuff, right? We're gonna do some more challenging stuff soon. This is just some basics, so we have, you know, starting base to build up. There is a homework assignment. Again, I asked you to do this thing with the prime factors, but there's a few more, some problems. If there's a lot of something, it's because they're easy. They shouldn't take you that much.